All right, so we're going to be looking at some examples where you actually put in some numbers. And so the thing on these examples is that you have some numbers in order to use the formula, but you don't have all of the numbers, right? So you have some, but not all. First thing is we do need a formula. So let's see what they're asking us for. And they're asking us for a delta G. So again, you're not going to have to memorize this. You just go look up your formula. So this would be that delta G equals, and then that's going to be a delta H minus T, T delta S. Okay, so let's look at this real quick. We need a delta H. Well, if you look over here, they gave us this handy chart, and that's delta H. So we should be able to find delta H from that. So delta heat of formation, products minus reactants. So that's something we can do. But they didn't give us anything about temperature, and they didn't give us any numbers for delta S. Now, what they did give us is they did give us the ability to find the sign, but not the ability to find the number. And so we'll talk about that here in a minute. So let's just go ahead and find the delta H real quick, because that is something that we can find. So delta H is going to equal my products minus my reactants. And so that was going to be, there's our products. So CO and Cl2. So CO is right here. And there we go, negative 110.5. So I'm going to go 1 times negative 110.5. And then we probably need to jump back over here and make sure this is balanced. I kind of skipped that step because I knew it was, but probably should point that out before. So we've got a carbon and one oxygen, and then two chlorines, two chlorines. So it is indeed balanced, but you would need to check for that, because if it wasn't balanced, that would be a bit of an issue. Okay, so back to our products minus reactants, and I'm going to add this to the chlorine. Now the chlorine is an element, so it's going to be a value of 0. So something like that. So there's your products, and we'll just put a bracket around that, and then subtract the reactants, which the reactants in this case are only the COCl2. So minus, that's going to be 1 times negative 220.9. Now I know that I know that most of this math is really easy. I'm just showing you these patterns because I do think that it's a good idea for you to continue to show all the bookkeeping, because if you don't, you start getting into some habits that are bad. So like, let's say that this wasn't ones. Well, you would need numbers here and here and here, and we don't want to get in the habit of not doing that. So anyway, I am putting in the coefficients even though they are ones. So all right, let's run this through a calculator, and let's get a delta H value. All right, so let's get a delta H value. So it should be pretty easy because it's a bunch of ones. So negative 110.5 plus 0, obviously not going to do anything, minus negative 220.9. So when you do that, you're going to get a value of, different pen. You're going to get a value of 110. So it's a positive 110.4. So delta H is positive. All right. So one thing we know is that delta H being positive is not usually a good thing for reactions. That doesn't help. So right now we know that delta G equals, and I'm going to put in my my delta H. So I'm using this formula up here, right? So I'm using this formula up here. So I got delta G, which remember delta G is going to tell us whether reaction is going to work or it's going to sit around and do nothing. So delta G equals, I'm going to put the plus sign in because it's important. So plus 110.4. And then we want to remember that this is in kilojoules per mole. And that's going to come into play here later, but this is, let me go back and fix that real quick. This definitely is in kilojoules per mole. Not going to matter on this problem, but it is going to matter in the future. So good habits. Okay, minus temperature, which we don't know, and then delta S, which is a problem because we can't get a number, but what we can get for delta S is a sign. So let's go up here and look at our problem. And so if you remember, you can predict the sign of S based upon states of matter. So if you're going, and I'll draw it over here, if you're going towards the gas phase, so there's the solid phase and liquid phase. If you're going towards the gas phase, then that's a positive delta S. And if you're going towards the solid phase, that's a negative delta S. So we are going towards the gas phase because, see, there's 1 mole of gas here, and then there's 2 on this side. So you went from 1 mole of gas to 2 moles of gas. And so that means that we're going to have a positive delta S. See, we're going towards more moles of gas. So what I can do is in my space here, I know that this is a positive delta S. I don't know the number, but I do know that it's positive. So now what's going to happen here is you're going to have to look at this and think about temperature and kind of think about what could happen here. So what can happen here is that you start with, and I'm going to have to drop it down here, and I'll just get a little space. So what happens is that you've got 110 minus a number, because if you look here, no matter what you put in for temperature, you're always going to be subtracting a number. So let's say temperature is like 5, and we'll just give delta S a value of 1. So then this would be 110 minus 5. Let's say temperature is 500, and we'll give delta S a value of plus 1. It would be 110 minus 500. So what you need to see here is that if temperature is little, you end up with a positive number. If temperature is big, you end up with a negative number. So what does that tell you? That tells you whether or not the reaction is going to work at certain temperatures. So what we would say here is that I'm going to slide, yeah, put this down here. We would say that delta G is positive or not spontaneous So delta G is positive or not spontaneous at low temperatures, and so in this case, we did, like the 5, but, the 1 would work, things like that. So at low temperatures, and then we could say that delta G would be negative or spontaneous at high temperatures. So this is a reaction that needs heat in order to work. It needs you to use the Bunsen burner, and it's not going to work like at room temperatures. You'd actually have to do something, but it could work. And if we kind of look at the variables, well, we know that delta H wants to be negative, and so we know that that this positive delta H is a problem. But we also know that high temperatures drive reactions, so a big temperature makes sense. We also know that a positive delta S is what reactions want. So what you have here is you have one variable, delta H, and that variable is not helpful for the reaction to work. And you have one variable, delta S, which is favorable. And so because you have one unfavorable one and one favorable one, it just depends on your temperature. And so you can figure this out. I've talked about this before, but when we have situations like this, go ahead and plug in a value. So plug in a value for temperature and verify. And so with the S, I just gave it a 1 because values of S are usually smaller. And so what's usually important is the sign. It's not usually super important what the actual number is. So, okay. Gonna pause this one here. I want you to try B. I know it's kind of buried in some stuff there, and I'm gonna erase some of that when I do that. But I want you guys to try B, and then go ahead and see if you can figure that one out. So